So I don't want to talk too much more about using eigen. I was intending to just leave that with you to have a look at the implicit thing in your own time. I mean, I know that many of you are NumPy or Fortran programmers as your main thing in the past. So I would hope that the use of that will be fairly straightforward for you. So the eigen is really good if you only need 1- and 2-dimensional arrays. If you need to go higher than that, it is less good. It does have some limited support for what it calls tensors, but its support is not full. So in that case, you're kind of on your own in terms of you need to find a library that is going to provide the features that you need. And there do exist several of these for higher dimensional arrays. There's one called ND array that does n-dimensional arrays. In fact, I think there are several by that name. I don't have any particular recommendations, I'm afraid. They're all okay at what they do. Right, where is my screen share? So what I want to talk about now is threaded programming. And where's my screen share gone? Great. Okay, so we have some material on using threaded programming, and this material is thanks to Mark Bull, who's at EPCC, who is one of our real experts on threaded programming. I am certainly no expert. I'm just sort of mid-level at threads. Mark, his primary expertise is the OpenMP stuff, but obviously all the issues around that also carry over to threaded programming as well. So this is based on material that he has done for us. Oh, sorry. Why is it not working? Okay, great. So, yeah, so this first part of it is quite short. It's just a brief introduction, how you go about creating and joining these threads, passing data into your threads, and synchronization. So the 11 revision of the language included an API for multi-threaded programming that's built in to the standard library. And it also includes a few things built into the language as well, most importantly perhaps being a standardized memory model, which basically means a language for the standard to talk about things like what happens before another thing, what do these concepts mean. And most of this you can safely ignore unless you are really getting down into the nitty-gritty and care about extracting every last ounce of performance from your threaded thing. But basically, the language adopted an API that is extremely similar to the pthreads standard that's part of POSIX. So if you've done any threaded programming on Linux or similar, you'll be fairly familiar with this. But instead of it being a sort of a function call based interface, it's a more object-oriented one. And it's pretty similar to the Boost Threads library that was developed throughout the sort of 2000s. Many of the C++ 11 and later features were sort of first adopted into Boost, and then the ones that were most widely used and most important tend to end up in the standard in some possibly slightly abridged fashion. And this is pretty portable. It does depend on C++ 11 support, but these days, pretty much every platform has a full C++ 11, at least, compiler. And these threads are represented by an object. And so to create a new thread, you have to construct one of these thread objects and to synchronize with them. There are various concepts like mutexes, condition variables, and atomics. You can also do tasking with these things via this async futures and promises concepts. Okay, so since threads are a resource, their lifetime is associated with an object. So this object is called stood thread. And you can create a thread by calling the constructor of this. And the things that you have to pass as arguments to stood thread are, first of all, what you want to get the thread to execute. So this is some sort of function-like object. So this can be just a pointer to a function, or it can be a full function object that you've created yourself, or it can be a lambda expression. And it's important to note that you cannot copy a thread, because a thread is a single resource in your system. So copying it is not something that most OSs support. They don't call. I'm just wary of misspeaking. I am not aware of any OS that supports duplicating a thread. I know you can duplicate processes with fork, but that's a different thing. So the thread API mirrors this logical behavior by disallowing copying, but you can indeed move a thread from one variable to another variable value. But I was sort of hinting at it here, going back to the RAII thing, the resource allocation is instantiation thing, saying that threads are created by the constructor. But unfortunately, for unknowable reasons, the standardization process did not attach the thread destruction operation to the stood threads object's destructor. So unfortunately, you have to make sure that you have called the join member function on a thread object before you delete the thread object. And what this join will do is it will cause the thread that calls the join operation to wait until the thread represented by that object has finished its execution, and, pardon me, the associated function object has finished its execution, has returned. So let's do hello world for threads. So to get access to this behavior, we need to include the thread header file, and then we've got input and output and vectors here. So let's start at main. So we are, first of all, we're making a vector of threads here, which is going to hold some number of threads. And what I'm going to do is I'm going to go around a loop 5 times. Each time round, I'm going to push back a new thread. So this is creating a thread, and I am passing to it this hello thing, which is a function. So this function type, this will refer to a function pointer, so it's going to be the address of this bit of code in your executable. And all hello is going to do is it's going to write to the output stream hello from thread, and then it's going to insert the current thread's ID. So the standard library includes a special magic variable, this thread, which represents the currently executing thread when you access it, and every thread can get its ID. Okay, and then we're doing an end line to flush the output buffer. So as we start making these calls, every time we call push back and create the thread, we're going to spin up a new thread. These are going to start executing in some way, and we're going to keep creating until we've done 5 of them. then we're going to finish that for loop and start this one. And this is going to do a range-based for loop over our vector of threads. And in each one, what it's going to do is it's going to call that threads join member function, which is going to pause execution here until thread 0 has finished, thread 1 has finished, and so on and so on. So we could equally well do this without defining a separate function out of line, since it's, you know, it's just a single line of code. This fits with the sort of guidelines I mentioned about how much code to put in a lambda. So let's just create the function object with a lambda here. So we've got we don't need to capture anything. We've got our body. Let's do hello from this thread and so on. And this code should be exactly equivalent. So a little word about thread IDs. So you can call getID on your thread, and there's this thread variable, which is what's called a thread local variable, and it's global for the thread, but not across the entire program. And every thread has this getID member that will return some number, and this is an arbitrary identifier. This is not a nicely indexed thing that starts at 0 for the main thread and goes to 1 for the next one, and so on. It might, and some executions of your program do that, but it is totally arbitrary and it's not reliable. And if you want to have sequentially numbered threads, you need to have some way of giving each thread a number when you create it, which is not ideal. So this isn't like your MPI rank or your OpenMP thread number, where you're guaranteed to have a nice starting at 0, counting up to the number of things you've got thing. So it's not terribly useful, except if you need to identify uniquely the current from amongst the current threads that are executing one thread. Note, this isn't going to be global necessarily unique for one thread during an execution of your program. So if you want to get some data into your thread, this is probably an important thing to do. So the arguments to the thread function are moved in or copied in. So passing simple arguments is really straightforward. If you've got a function that takes 2 integers, this is going to work exactly the way you would expect. The values of A and B are going to be copied in this case, passed into hello, and away you go. And then you can just run it and join it as you would expect. But if you want to pass a reference in, so for example, this hello function is going to increment the variable x, we need to do something to avoid the thread constructor copying for us. So to do that, you need to pass a wrapper object that helps with this. And this ref function is a convenience function that will take the value that you pass to it and return a wrapper object that allows that wrapper to be passed by value into hello, and then the thread's implementation will unwrap that inside the new thread and pass by reference into the actual function for you. And then if we start at 9 and we pass this value in by reference wrapper, it will be updated for us, and x will have the value 10 here, as you would hope. So okay, let me so passing x directly here will indeed, inside the new thread, you will get a copy of x. You will get a variable that is local to the thread. Okay, so this is a defensible design decision for the threading API because shared state is can often be problematic. So shared state means that you, the programmer, have to work harder to manage that, to ensure that it's accessed safely, there's no synchronization issues, blah, blah, blah. So adding an extra step to enable use of shared state is a perfectly reasonable thing, in my opinion, from a software engineering point of view, because you're saying, okay, I know that I need to be dealing with a reference here. Let's just do that. So the threads, yeah. So there are two functions signatures that need to be considered here. There's, first of all, there's the threads function interface, and then there's the function objects that run inside the threads here. So what's really going to happen at some low level is it's going to go down through several layers of API, and at the bottom level there's going to be something that says to the operating system, you know, pthread create or equivalent, to start a new thread, and it's going to have start that on some internal C++ runtime function to start a new thread that is going to have some custom data attached to it somehow, and that's going to know, okay, I need to call whatever, and that's going to run a bit of code that will set up and then go in and call the function that you've asked it to call to run in the new thread for you. So there's going to be a little bit of extra stuff going on in between here, and that's going to deal with packing and unpacking these reference wrapper objects for you. Does that make sense? Okay, great. I'm happy to take any other questions, whatever, later. So I sort of alluded to the synchronization issue in what I was just saying in response to that. Because let's suppose we've got a type that represents your wallet, you know, let's go full blockchain. No, let's not. So this is just some class in our application that represents an amount of money that some user has. We'll start off at 0, but then you can call this add money member function. So if two threads call the add money member function on the same wallet object, then there's what's called a race condition, where each thread is going to have to read the value of money from main memory into its you know, its cache, and then into its registers. Then it's going to have to add the amount, the right amount onto that, and then it's going to have to store it back to main memory. And so you've got this read, modify, write cycle, and if two threads are doing this at the same time, there's a chance that they could both read the old value, both increment that correctly with some value, and then write back. One would overwrite the other updated value, and so you would have lost a bit of money, or something even weirder could happen where the value that gets written is just totally garbled. So you can use what's called a mutex to protect this. And mutex is a short form for mutual exclusion. And this allows updates to share variables in a protected fashion. And if your object has a number of member variables that need to be protected, you can quite naturally declare the mutex inside that object. So we've got this stud mutex here, and it's declared inside the class. And when you want to modify your current balance, what you can do is you can say mutex.lock, and that will do whatever is necessary to ensure that the currently executing thread and only the currently executing thread own the lock at this point, then you can update your money variable safely, and then you can release the lock that you've held with the unlock call. So I hope you've all spotted that this is a resource, this mutex, holding the lock of it. So this says, the RAI immediately says to us, okay, this is a resource. You need to tie its existence to the lifetime of an object, because you need to make sure whenever you lock one of these things, you really have to make sure that you then unlock it. Otherwise, you're going to get a deadlock type situation. And handling this in a general way can be quite tricky, and doubly so if you end up with exceptions. So the language standard includes this lock guard class that implements RAII type ownership for these mutexes. So when you construct a lock guard, you have to pass the mutex in as its argument to the constructor, and it will ensure that it has locked the mutex for you. And then the destructor of the lock guard will release the mutex back for use by any other threads. So how would you do this? So first you need to make sure you've included the mutex header. Got our mutex member variable here. And then in the member function that modifies it, we first create a lock guard on the mutex. You'll notice that lock guard is a template here. Okay, we're creating it on the mutex that's our member. We then perform the update we need in total safety, and then when the program's flow hits the closed curly brace, the lock guard is destructed, and the mutex is therefore unlocked for further reuse. So this is fine. This is stuff that you have to do if you're doing threaded programming sometimes, but there is a slightly higher performance and simpler view that you can take, because most modern hardware, for many of the built-in, the hardware supported data types like integers, floating point numbers, and so on, provides special instructions that can do these operations atomically for you. So you can say, okay, to the integer stored at whatever memory location, atomically get that, add a number to it, and store it back. And C++ provides a view on top of these very low-level hardware instructions called std atomic. And this has specializations that support these operations on the integer types, Boolean types, and when you can finally move to C++20, you can do this on the floating point types as well. And so what does this look like? So to create one of these atomic variables, you say it's a std atomic integer in this case. It's exactly the same as before, and you initialize it, give it a default initializer of 0. And then when you come to add some money to this wallet, you go money plus equals this, and it is exactly the simple code that you've had before, except that the compiler understands these types and can insert the necessary special hardware instructions to do this read, modify, write in atomic fashion, in a way that guarantees that no other thread that is also using atomic instructions will be done safely. So you have to remember that you mustn't be cheeky and get the address of this and then treat it as an integer to do an end run around this. As long as you only access the variable as an atomic, you're going to be great. So when you're thinking about how to create any classes that are going to work in this world, you need to think about a few things. So you can always add a mutex data member to the class, and make every function that accesses the sort of the mutable state of this thing acquire and release the mutex, for example, using a lock guard. And this is an okay design in the sense that multi-threaded code can use the class without worrying about the synchronization too much. But it can result in quite a lot of overhead because you've got a lot of locks and unlocks happening and synchronization when it's not needed. So you do need to think rather carefully about how you're using this in your application. Okay, so that's just a sort of some gentle warning here. Okay, so this thread stuff comes in two parts, and I'm going to go through both parts, and then we'll have a little look at the threaded programming exercise. So what I want to talk about here is sort of asynchronous tasky type things. Let me get make sure I can see this on either screen. The parallel template, the parallel algorithms now appearing in the template library, and a little discussion about using threads versus OpenMP. Okay, so first async and futures. So if you're using std thread, there's no way to get a return value from the function that ran in the thread. And you could always alter this to use, for example, an output reference argument to store its output. But this is problematic because you're having to change the API of the function that you actually want to run in a thread. If you've got a nice function that takes a bunch of parameters and returns an answer for you after doing some moderate size calculation, you would hope that you would just be able to just assign that to a variable as normal. But threads don't support that, unfortunately. So one way around this is to use this std async thing, and this is will give you what's called a future. And in addition to this, this way of programming with threads allows the exception handling machinery to work properly if you actually throw a thread. So when you call std async, what it returns is what's called a future object. And then when you call the get function on this return value you get, this is going to block until your the function object that you passed into async has returned a value and made it available to you. So let's do an example that makes it a bit clearer here. So we have an add function, okay, it's just going to add 2 integers for us. Obviously, that's a very silly thing to deal with all this extra boilerplate, but it lets us not worry about those details. So we got our arguments. So to run this in an asynchronous fashion, we just call std async, which creates this future object, and inside the future there will be add, which is the function that wants to be run, and then its arguments. And in somewhere inside this machinery, the runtime will deal with invoking the add function with those arguments for us. And so the value that this is going to return is of actually type future of int. So the future is a template class, which I hope should be clear to you from this syntax. And the template parameter that you use here tells the type system what type is expected out of this function. Now, obviously, you could just use auto here and let the compiler figure it out, because async will return the appropriate future for us here. And then we can, at some point later in our program, call future.get to write what the sum of these two numbers is. And this function called get will block until the function object that you passed to async has executed and returned a value, or thrown an exception, in which case future.get will throw an exception for you. Yeah, so like I was saying, you could just use auto here instead. So there's a few issues with this. The first is that by default, the runtime, the C++ runtime, can decide not to actually create a thread for you when you run, start it, and it can simply wait until you call future.get to execute the code. And if you have anything that has synchronization going on, this can give you a deadlock. So one thing you can do is you can force asynchronous execution of this thing by supplying an extra argument to the async function. And this is going to force the runtime to run that function in a new thread asynchronously. So the standard explicitly does allow implementations to choose to use a thread pool to execute this, but pretty much all of them don't. And so you can end up, if you start a lot of asynchronous futures going, you can end up with way too many threads for efficiency going on, and you're also going to incur the sort of penalty of the thread startup and teardown going on. So, of course, this is C++, so you can always write your own thread pool, and there do exist libraries that will create a thread pool for you. So basically, you can call std async with a custom thread pool object here, and that will do the right thing for you. However, writing your own is a non-trivial piece of programming, so I wouldn't recommend it until you've had a bit of practice doing this sort of stuff. Okay, but the C++ 17 has introduced us some things that can really help with this, and this is a revision to the library that incorporates parallel versions of many of the algorithms that exist. I need to update these slides because the parallel STL is just about available in most of the standard libraries now. There was unfortunately a very long lag in terms of the main open source standard library implementations supporting parallel algorithms, but it's pretty much there in the latest revisions now. And what this does is it adds to many of the algorithms that we talked about, was it yesterday? It adds an extra argument that is the first argument to these template functions that takes what's called an execution policy argument. And there are 3 coming on to 4 of these available, which specify how to execute the code in the function objects that you've how to execute the algorithm. First is a sequential tag, and this says execute it in a serial way in order. Then there is the parallel one, which says execute these things in parallel, but one at a time. Well, in one at a time in a given thing. And then there's parallel and unsequenced, which means vectorized in C++-E's. And then C++20 added a do this in a vectorized or unsequenced way, but not necessarily parallel across multiple threads thing. And that was added in the 20 revision. So how might you do this? So let's say we've got a vector of integers, and it's a large one that we've generated somehow. So we can do this in several ways. First of all, we could just do a standard sequential sort without any thing. And in principle, this is now up to the standard library to choose what execution policy we're doing here. We can say explicitly that we're going to be sequential. We want to guarantee that this is done sequentially. So we pass in the std execution sec, meaning sequenced. Execution policy is the first argument. And then we want to allow and request execution in parallel by doing this par one. And then finally, we want to allow parallel and vectorized execution here by using the par unsec execution policy. So these are pretty easy to use. You just need to add this extra tag, and stuff is going to happen in parallel, hopefully. And so for algorithms that you use, you, the programmer, need to take a little bit of care if you're going to use these. So if you're passing in a function object argument that, for example, operates on each element, it's up to you to ensure that this is going to be correct if you run it in parallel or in a vectorized thing. And this basically means that if your function object was doing something cheeky internally, like keeping account of updating some variable at an outer scope to, say, keep track of the number of times it was run or update some other state in the background, that is likely to become incorrect in this new world. And the other thing that this doesn't do is it doesn't give you any control. Okay, so it doesn't let you say, how many threads should I use? Which threads are going to handle which elements? And you know, how to, you know, are you going to decompose this that element by element in a round robin way, or are you going to use blocks? You know, is this going to statically or dynamically assign work to threads? For example, if some elements in the range are going to take more work to do than others, you might want to have a dynamic thing implementing work stealing or something. And also, you know, you, the programmer, might know something about which cores on your chip are going to have faster access to which bits of the data, for example. So data affinity, locality can be a problem. So it's up to implementations to support additional execution policies. And indeed, some of implementations of the standard library do this. There's one called HPX, which is from a large research group in the States that's interested in this sort of parallel programming with C++ world. And they have execution policies that you can create based around thread pools and with static scheduling across threads of the index space and so on. And perhaps even more notably is in the last few months, NVIDIA, the GPU making company, have created a version of the standard library that will offload your computations to the GPU. So if you have a GPU attached to your system that you want to parallel, and really your parallel parts of your algorithm can be expressed using these sorts of algorithms, then you may as well just go ahead and start using it because it's going to work fairly well. And the nice thing is that then if you're not on the GPU, you can just stop using NVIDIA's, you can add some nice little type defs to not use NVIDIA's fancy execution policies, and it will still work on your CPU-based programs in some way. It won't be as fast, obviously, but it will still work, and it will be very portable. And you know, the standard is thinking about ways to add more support for these in future revisions of the language. And there's work going on around what is called executors to enable more detailed control over how to execute these parallel algorithms. So threads versus OpenMP, and I apologize, are there people here who do not know what OpenMP is? If you could raise a hand on the collaborate thing. Oh, great. So you all know what OpenMP is. Great. So OpenMP has for a long time supported C++ as one of its base languages. It's worth thinking about whether it's worth using threads or OpenMP if you're in the domain when OpenMP is quite good. And OpenMP 5 now supports most of the features of C++ 11 and 14, and I think I saw yesterday they've released a draft of the next revision of the standard that is going to have even more support for C++. So things it doesn't, OpenMP explicitly doesn't support are C++ threads and atomics, which is entirely understandable since OpenMP has its own ways of doing those things, and interoperating with those might be non-trivial, let's say. So if you are really committed to C++ and doing everything the C++ way, OpenMP is not going to work terribly well unless you simply want to speed up a few loops. But that's worth knowing that OpenMP has lots of useful features that are not easily available in C++. So first of all, barriers. Okay, so these have indeed been added in C++ 20. And so a barrier is a function call that will basically wait until all the threads in some group have reached that point. There's various things about thread pools and tasks. And again, this is a work in progress, and it is not in C++ yet, but people are trying to get it into the next version. So parallel for loops are extremely easy to express in OpenMP, and stood for each can be parallelized. And if you don't need the detailed control you can get with OpenMP, that may well be good enough. SIMD directives, which is where you say something like pragma omp SIMD, which will use these vector instructions that can operate on multiple elements at once to speed up a loop. And these will actually probably work just fine in C++ threads. Really, I would say that the OpenMP SIMD directive is the easiest way to get control of how loops get vectorized in your programs. Okay, but sometimes you need some behavior that is not trivial, is not easy to do within OpenMP, or in fact may be impossible. And the C++ threads has all the building blocks that you'll need to implement any of these features yourself, or you could borrow some existing implementation that's available on GitHub. And then you can do all the nice C++ programming to make everything look syntactically neat. Okay, but again, so this is not guaranteed to be correct because low-level threaded programming is hard, and you will have to go off and do the testing or rely on someone else who's done the testing for these things. And it's going to be hard to make this portable and very efficient, because maximum efficiency typically requires some sort of architecture-specific configuration. Okay, and what about GPUs? So OpenMP does have support for offloading to GPUs. You know, it's starting to get there now. I think the OpenMP target stuff is starting to get quite good, and the standardization process for C++ does want to get there in some way. The route that C++ is taking is based upon what's called SYCL, that's SYCL, which is a sort of enhancement to the language to support heterogeneous programming. I think SYCL is very interesting and powerful, but it is not part of standard C++, although one of the nice features of SYCL is that it does not extend the language syntax. You can write a SYCL implementation that is simply a library. And so if you just want to run on CPU only, you don't need to have a fancy compiler. You can just get a SYCL implementation that you can run inside your compiler. I do not know if any of those are any good. I have to honestly answer. Most of the good SYCL implementations do require a compiler extension. And there's also a bunch of C++ frameworks for programming your GPU as well. So things like Cocos, which is I like a great deal. Raja, which I know very little about, I'm afraid, and SYCL, which I just mentioned there. And that's a bit more formalized, standardized, because there is a standards body that's working on that. It's just not officially part of the C++ international standard. Okay, so, there's various issues around OpenMP which make writing idiomatic C++ harder. So, for example, you can't have a private or reduce over a data member of an object. Reductions are handled in quite a different way. OpenMP has a fixed model of how you fork and join the threads. But that's not necessarily a bad thing, because the model that OpenMP has chosen is relatively easy to implement in a high performance manner. And C++ has no standardized way of binding particular threads to particular cores inside your hardware. If you're writing C++, standard C++, there's no way to guarantee that your threads won't move around between your cores and then move further away from their data. Okay, so for example, the simple if your program is executing up this graph, it's serial, you hit an OpenMP directive and it forks a bunch of threads which do some stuff in parallel, and then at the end of that parallelized region, all those threads join and you go back to a single thing. That's the sort of canonical OpenMP way, and it does support what's called nested parallelism, where each one can run a bunch of threads and then close them. But you can't do this more complex parallelism where each region is not strictly nested inside another one. So if you need a pattern more like that, you can't use OpenMP at all. Okay, so right, thanks, great. There is an exercise about threads, which I suggest you have a look at. This is now it's in the Git repository that we've been using all along. And the file area.cpp has an implementation of computing the Mandelbrot set. So, sorry, apologies. This assumes that you are currently taking our MSc the way it's been written. So we have a course that students would take before this one called Threaded Programming, where they would learn about OpenMP. And during that course, they would parallelize a Mandelbrot set generator. So what we suggest you do is that you parallelize the outer loop of the main computation using threads. And so you could try doing this either with a separate function or with a lambda expression, as you prefer. And suggest that you try several different ways for synchronizing the update to the shared counter, because this is computing the area of the Mandelbrot set, I should hasten to add. So you could try it with a mutex and a lock guard, or using an atomic, and measure the difference in performance in these cases. So are there any questions about the material, or do you want to just crack on and try it? Oh no, sorry, I haven't updated this for Archer 2. It's assuming you've got Intel compiler, which is was available on Archer 1, but now because Archer 2 is AMD, this doesn't work. You'll need to so I suggest you set CC just to G++ here. You may as well put just O2 or O3 there. Okay, so I'm being asked a question about a vector of queues. So what's the right syntax to add a new empty queue into a vector? Okay, so if you've got a vector and you will call pushback on it, you need to supply a value of the correct type. So if you've got a queue of ints, like you're using here, supplying simply the type name, std queue of int, is not going to be correct. That will be an error because you need to supply an instance of that type, not the type. And so, yes, creating an empty queue means you need to call the constructor of it. In this case, the default constructor should be fine to make an empty queue. Does that answer your question, Long? Great. Okay, so of course I'm happy to take questions. I'm just going to unshare my screen for 15 or 20 minutes, unless it's helpful for a question, to give you a chance to try the exercise for yourselves. But I'm not going anywhere. No, there's no more lecture material today. I know there is another lecture in the material. Feel free to have a look at it in your own time and ask me any questions. It's about using the CoCos library to program GPUs. If you have access to a GPU, go ahead and have a go at it. In fact, for the early parts, you don't have to have access to a GPU. Because this course isn't primarily about GPU programming, we're not going to do it, but the material is in a repository somewhere internally for us that all comes together. So I thought I would leave it in for anyone who's interested. If you want to play with GPUs, you can always sign up, do the Cirrus driving test and request access to the GPU there. Although that is a one-time in your career access for driving test access. But feel free to use it if you want to play with those things. Great, thanks, Killian. I think the lecture recordings will be made available at some point. I don't know the details. You know, in case you're like, what on earth was he saying about threads? I've forgotten it. You can go back and find out. But we're almost done. So I thought I would just very quickly have a look at the doing this in parallel exercise. So there's several things we need to think about, and a lot of the questions that people are asking hint at this. So it's, first of all, you've got to choose how you're going to split your square of the Mandelbrot set up amongst the threads, and then each thread inside, and then you've got to think about how you're going to do the updates of the variable num inside. How are you going to update that to the different from each thread running potentially in parallel? How are you going to update that back in the main thread? How are you going to get the right answer there? So for doing if you were doing OpenMP, all you'd probably do would be stick a pragma, if I could spell pragma omp parallel 4 here until it's collapsed the two loops together, and then you'd have a reduction on num inside with plus, or how I forget the syntax because I don't do much OpenMP. So that syntax is probably not correct, but that's roughly what you might do. You might further do a thread private variable for the local count, and then at the end of the parallel region update that. That would be another very reasonable thing to do. And again, if you are doing this with threads, that is probably also what you would do. You would probably have a thread local variable that computes the local sum, and then you would do, say, an atomic addition onto the total, which you could have declared as a std atomic. Another possibility would be to declare a vector or an array of these things, and then have each thread update its own value and store it into array, and then call something like std accumulate or std reduce back in the main thread to add up those sums. There's nothing particularly wrong with those things. The only problem with using an array or a vector for those is that those values will be packed right next to each other in memory, and if you have multiple threads writing to the same memory location that lives on the same cache line, this is going to be what's called destructive interference or false sharing, and you'll get pretty poor performance for those writes. So if you were doing that, you would have to take care to ensure that each value is at least one cache line away from the next one. Otherwise, you'd get terrible performance. But let's go ahead and do this. So let's say I'm going to split up my I index into chunks, and I want to have a certain number of threads, which I'm just going to set to be 8. Say const int, sorry. So I'm going to need somewhere to store my things. Someone was asking about const extra earlier, and this is really just an extra level of constantness. This says that whatever you initialize with it is going to be a constant expression, which means something known at compile time. So since I do know it at compile time, I can do that. And that means I can use it in places where you have to have a compile time constant. So I can have an array of threads here. I've got my workers. And then I'm going to need to create these workers somehow. So let's do T for thread. Okay. So I'm going to have to make a thread, some function. Let's say we're going to do a thing. So we've got a thread ID that we're going to pass in here. And then we're going to have some body that I'm going to figure out. And then I'm going to pass in T to that there. And this thing needs to get stored in my workers array at element T. Now, obviously, there's no body in this. It's totally useless at the moment. And then when we're done, we're going to need a loop to join these threads. So we've got by mutable reference to the threads for each thread in the workers, we call T join. Okay. And then that will clear up. So obviously, I've done the sort of thread startup and tear down here, but I've not actually got anything happening inside the parallel region. It's all still happening here. So the J part of the loop is fine. Okay, if I'm just going to split it up over blocks over I, this part is fine. Again, I was mentioning that we're going to want some sort of local count for what the number of points that are inside the Mandelbrot set is. So let's have a local num inside, which I'm going to start off at 0. And I'm going to update that one inside my loop. So this, if I set j correctly, will do one line through my Mandelbrot set area computation. So that's something. And then we're going to need, we're going to need to do an update of the global num inside gets updated by the local one. Okay, so notice that's a different variable from the one before. So let's go that's an atomic integer. I'm going to start it off at 0, and we can now use it here inside. Okay. So all we need to do now is we need to do the working out of the what the correct I is going to be, and we're going to have to also do another loop over I, over the local bound. So if I'm on block number T of it split into 8, I need to work out what my start and ends are. I'm going to call it low and high because that's shorter to type. So my starting point. So first of all, let's work out what the block size is. And that is going to be the number of points divided by 8. So I'm going to have to be careful. Is this 2000? Is this divisible by 8 exactly? Yes, it is. But in a more general case, it won't be. So let's do the arithmetic correctly. So this will give us the right number of blocks. So the starting index for this block is going to be the block size times the thread ID that we're on. And the end of this loop is going to be block size times the thread ID plus 1. But it's going to be smaller of this and the number of points. Is that right? Yes, it's going to be the minimum of that endpoint, because if it doesn't map on exactly, if the number of points is not an exact multiple of the number of threads, we're going to need to do that. And now we can do our our I index for this goes from low up to, but not including high, and it goes up by 1 each time in the loop. So and actually closing the I loop there would be helpful. That's that one there. Okay, then now that's empty, I can delete that. Then we need to join. Okay. Right, I wonder how many errors I've got here. Let's see. Quite a lot. What am I doing wrong? Have I included atomic? Yes. initialize it by construction for the value, okay. End thread was not declared. Yes, that's because I can't count. Okay, fix those. Yeah, I've not been very good about spelling today. Okay, so now we're getting an actually worthwhile error. So I've forgotten to capture that local variable. So I do indeed need to capture the atomic global count, and I need to make sure I'm capturing that by reference. And endpoint is not captured. Okay, that's also a good point. Shift isn't captured. What's shift? Shift is a complex number. I could capture that by value or by reference. Let's capture it by reference. Okay, so we've got a lot of things we're having to capture. So what we could do is we could set what's called a default capture specifier, which says to the compiler, if there's a name you don't know, just capture it for me and capture it by default. Capture it by reference in this case. If I wanted to capture by value by default, I would just use an equal sign, but I'm going to capture by reference. And I've got one more error. Num inside was not declared. Okay, yes, that's because I changed the way that was done. Now I think that's going to complain at me. Oh no, it's not. Okay, does anyone have a benchmark for me? Did I beat it? Has anyone got a number? Run it a couple of times. Sometimes you get a faster result the second time around. About 2 seconds. So with debug, that's hard to say because I'm going to set that to fast because that will be even better. Yeah, using the fast math stuff has got it an extra 5% or something. Okay, well, it's a lot better than 56 seconds. So I'll put, like I said, after I've had my lunch, I'll put some solutions on the GitHub for everything. I think my email address has been on the slides and stuff. So if you've got any questions, I'm very happy to try and answer them via email. Or you can do it via GitHub issue on the repository if you prefer. Anything you like, I'm happy to answer questions over the next few weeks about anything in the course, or if you want any pointers about next steps or questions about how you might apply some of these things in your particular application. I'm happy to have brief conversations via email or fix up a Teams or Zoom call or whatever. So yeah, so Claire, who runs the training for Archer 2, is going to definitely be in touch asking if you could please fill in a survey to tell us what you thought. So, very happy to know anything that you think could be improved about the course. Like everything, this is a work in progress. So thanks to Archer2, and thank you for organizing all this, and thanks very much everyone for the really excellent questions and engagement. Yes, Mohammed, like I said, I will push this to the GitHub via on a branch, just so that people don't sort of accidentally see the solutions if they want to have a go themselves. Yeah, so thanks everyone. It's been a pleasure to talk to you all with the very many questions and comments that people have made. That's great. Unfortunately, with online lecturing for our MSc this year, it was very much like lecturing to a silent room, and this has not been like that. So goodbye, and thank you very much, everyone.